Hello,
Yes, Blasius, how are you?
Yes,
I'm
hello.
good. How are
Yes,
you?
please.
Are we fine?
Yeah. Okay, so um, we need to start now. Okay, so we have to look at number systems and their conversions in this lecture. Let's kickstart this. Okay, so we're going to be looking at some terms first of all. Um, bit. Let us first of all look at what bit means. So bit comes from binary bit. I mean binary digit. So when you have by and then we add a t, that's when we get the word bit. So this means that it is just the smallest information or the smallest unit of information that we can have as stored on a digital system. So it can either be a zero or a one. So when we say what a bit is, you can say a zero is a zero. A bit can either be a zero or a one. That's what the bit means. So if I get like 4 bits, maybe if I just say I group them like this, then this gives us a nibble. So a nibble is a group of 4 bits. Then a byte is a group of now 8 bits. For example, if you have this group, this is one what? 1 byte. Okay. Yeah. So then a computer word. A computer word is a string of bits whose size is called a word length and is fixed for a specific word computer. So if I have maybe some string like I have some string like maybe Stewart, even though this is the string that I'm writing on the computer, it will be stored in terms of um, binary. For example, assuming this will be the value for S and then another value for T, another value for U. So ideally, everything will be stored in terms of bits. So for you to call it that this is a computer word, you need to know that there are very many bits. So that's why we say that it's a string of bits, but whose size is actually known. Yeah. So we have talked about already nibble. Um, okay. Yeah. So before I proceed, is there anyone who has a doubt on this? Can I echo something? Please, you just speak up. You have a doubt? Yes, no?
Can I go?
Mm-hmm. Yes, please.
Yes. Yes. Good evening, sir.
Good evening to you. How are you?
Hello. Can you hear me?
Yes, please.
Yes. Mine is not a doubt. Mine is not a doubt, but it is totally lost.
Hmm. From where?
Uh, I want to say what I don't understand where these things, where everything that you have started, I'm completely motherfuck. I was saying that I'm very totally out.
Mm-hmm. So let me ask, how many lectures have you attended for digital
This
electronics
is
so
the
far?
second one.
This is the second one.
This is the second one.
Okay. Um, so this topic is under number systems. Okay. We are going to look at
Mm.
different number systems. Like if you have heard the word base, a base. Have you heard about a word a base before? Like base 2, base
Yeah.
10, base 8, base 16. Okay. That's the topic that we're looking at today. But
Yes, I'm getting you.
I first decided to talk about some common terms that we might be using later. Okay. So when I said that a bit, I was trying to explain what a bit actually means and where does it come from. And I said that the bit itself comes from the word binary digit. Binary means a base 2. Okay. Binary means a base 2. And I say that the word binary itself, I mean the word bit itself, you just assume that if you have the word as binary digit, and then you try to just um, use the by and then the t, it means that that's when you can combine and then say this is a bit. Okay, it's just like a short form of binary digit. And then I said that a bit can either be a 0 or a 1 because base 2 only carries two numbers. The set is only two numbers, a 0 up to 1. You cannot include any other number like 2. Okay? So a 0 is a bit and a 1 is a bit. That's about the bit. Then I said the byte is a group of 8 bits. Assuming if you have a group of 8 bits like this, any group, because these are 4 and these are 4, this is, we say that 8 bits always are equivalent to 1 byte. Okay? Yet I also talked about the nibble and I said a nibble is just a group of 4 bits. Assuming I write this is just a group of 4 bits making to a nibble. And then later, I talked about a computer word. I said a computer word can be a string of bits whose size or word length or word size is actually fixed for a specified computer. So this can vary from computer to computer. So the word length may equal to 1 byte, 2 bytes, 4 bytes, or be even larger. Okay. Yeah, so that is what I was talking about. So does that help now? Hello. Okay. So kindly when you ask, like, try to stay in and then now you get the concept as you had required. So okay, just a second. Okay, so um Let's continue. So let me talk about complements now. Complements in binary, I mean, in number systems. So what is a complement? Um, to complement something, for example, if I have a number, let me say number x, and I say I want to write the complement of x, then the complement of x, ideally from your algebraic math, I think you would write something like this. This means a complement. So you are like overturning something. Now, this is actually what we call the ones complement in our complement aspect here. So if I have a binary number like this, and I say I need its complement, then I would just change the ones to zeros and then the zeros to ones. For example, this one, I would have 0, 1, 0, and 0. Then if I had another number like 1, 1, 0, 0, okay, 1, 1, 1, 0, and maybe 1. Okay, I want someone to interact. Uh, Bernard, are you able to talk?
0, 0.
Hello? Please, if I've not called you, please don't unmute your mic. Bernard, are you on? Okay. Jean, are you on? Jean Manala.
Yes, sir, I am on.
Okay,
Following you.
please, yeah, try to interact. Can you tell me the complement of this number?
Not, not, sir. Not for now.
Not for now. Okay, so who is able to contribute? Who has understood what I'm trying to say here about the complement? Edrin.
Yeah, hello sir.
Yes, please.
Myself Johnny.
Yes, please.
May I try to contribute for that compliment?
Okay, yes, please.
When you see one, you put zero.
Mm-hmm.
When you see zero, you put one. That is formula.
Mm.
So in this question, you put zero,
Mm-hmm.
zero,
Mm-hmm.
one,
Mm-hmm.
zero,
Mm-hmm.
zero,
Mm-hmm.
zero,
Mm-hmm.
one, zero. This is the complement of this number.
Is that right? 0, 0, 1, 0, 0, 0. I think
Yeah,
it's is it all? I think it's incomplete.
yeah,
Something is incomplete. I think it's incomplete.
yeah.
Okay. Yeah. So what about can you try this one? Can you try this?
Which one, sir? In
This one
this,
here.
this, okay.
Hmm.
In this one, you get one.
This one here. We are changing this one to a one's complement. Uh-huh.
Can I try, sir?
Blessings.
Okay, yeah,
Let only one person talk at the moment. Okay.
This is Michael.
Mm-hmm.
Uh, to me, that number will be a 000
Mm-hmm.
11
Mm-hmm.
000.
Yeah. So the rule is that if you want to make a ones complement of a binary number, you complement all its elements, all its bits. So to complement something, like I said, if you had a number x and you want its complement, just invert it. The bar that I wrote here just shows that I've inverted it, okay? So when you invert a 0, it is always going to a 1. When you invert a 1, it goes to a 0. So in any binary number, that is what we do, and that is what we call the ones complement. So there are other types of complements that we are going to be saying, but the ones complement is computed like that. So in the example, in this slide, is this. The number is 1 0 0 1 0 1 1 0. If I want its complement, then it will become 0 1 1 0 1 0 0 1. Okay, that is about the ones complement. Is now is that now fine, Jean?
Yes,
Okay,
it is now fine.
okay. So before we proceed, we are going to again be looking at, at other things like uh, MSB. At the moment, let me first talk about MSB. For example, in this number, the MSB is going to be the first number from your left side. Then the LSB is going to be the last number or the first number from your right hand side. So LSB in full stands for least significant bit, while MSB stands for most significant bit. We have already talked about bit, and we know now why we say bit in this case. Okay, if it was just a number like maybe 23, then we wouldn't say that 2 is MSB and 3 is LSB. No, this would be wrong. This one would be now termed as um, just a digit. So we could say that this would be MSD, most significant digit. Yet this one would be LSD, least significant digit. Okay, so let's move ahead. So we have seen and we have tried to understand about the one's complement. So our goal is going to be focusing on four different what? Four different number systems. So four number systems. So we shall be looking at the binary number system, um, the decimal number system, the octal number system, and the hexadecimal number system. So each of these numbers have two complements, two complements type, two complements. So for example, binary, which is base 2, will have always um, a ones complement and a twos complement. Decimal, which is base 10, will have a nines complement and a tens complement. Base 8, which is octal, will have a sevens complement and and an eights complement. Base 16, which is hexadecimal, will have 14's complement and 15 and no, not 14's. It is 15's complement and 16's complement. Okay, sorry about this. So this will have 15's complement and a 16's complement. So we have to look at all these complements and see how they actually computed. So far we have looked at the ones complement. Now let us move to the twos complement. So the trick is not so hard. If you want to compute a twos complement, just something you do is, first of all, first step is, let me say step one is, first of all, get one's complement. So get its one's complement, and step two, you just add a 1 to to um to the one's complement. Okay, so this brings a question in your mind. Since we are dealing with binary, how do we add? How do we add? If we add, if I was adding, let me start with showing you this. If I was adding just like in decimal, like maybe 23 plus 10, of course I would have a 3 here, and I would have what? A 3, right? What about if I wanted to add binary like this? Let me start with this. What would I have? I would have, let me actually just say, if I wanted to add a 1, 1, and then a 0, 1. So 1 plus 1, um, 1 plus 1 would be a 2, okay? But we cannot write 2 because this is what? Binary. So we cannot write 2 there. So what do we write? We write a 0, okay? And then we carry a 1. Ideally, we would have written a 2, but because 2 in binary is actually written as 1, 0, so we write like the 1, I mean like the 0 and then carry the 1 the other side, okay? Because we couldn't now write it here directly. So we just write the 0 and then carry the 1, okay? So when we carry 1, still here we have 1 plus 1, which is a 2. Again, we cannot write a 1, 0 directly. We have to write a 0 and then carry a 1. Of course, now this is a 0. Automatically, 1 plus a 0 is a 1. Now this would be the answer. Okay? We can prove this. We can prove this. If I could convert this, 1, 1 is a 3, and I know 0, 1. What is 0, 1? This is a 1, which is a 4, okay? 3 plus 1 is a 4. And then if I compute this is also a 4, okay? So this is a 4. So in decimal, so this is just fine. So at the moment, don't go into the hard concepts of knowing how to convert from binary to decimal. We shall learn that. But just try to understand that whenever you see you are adding a 1 plus a 1. You cannot write 2 in binary. You only have to write a 0, then carry a 1 somewhere, which you will now again compute later. Yet if you have to add 1 plus a 0, of course, that will be remaining with what? A 1. That will be a 1. So if that concept is home, let us now go back to our computing of the two's what? Complement. So we said step 1, you get the 1's complement, then again add a 1 to a 1's complement. Aha. Let me give an example here. Assuming I say that we need to have a 1's complement of, I mean a 2's complement of this number. Step 1, I would say get the 1's complement. So 1's complement will be what? It will be 0, 1, 0, 0. Then add a 1, which is step 2. Add a 1, so I would have now 1, I mean 0, 1, 0, 0 plus a 1. Aha. So 1 plus 0, I would say I would have 1. 0 plus 0, that would be 0. 1 plus 0, 1, and 0. This now would be called our two's complement. This will be the two's what? Complement. Okay. Assuming we have a number. Let me have some other editor here. I think I'll use this. Before we look at the example, Komuhimbo, are you ready to interact?
Yes, I'm ready to interact, just that I came in a little bit late, so I did not see the first, but I'm ready.
Okay, so don't worry. So we are doing a two's complement now. We first completed the one's complement. Just for your review, we said one's complement is just inverting a number to get its opposite. We are starting with binary, and binary only has two numbers. Okay, set is 0 and 1. You cannot include 2 because this is called base 2. So when you talk about complementing, if I want to complement a 0, it will become what? A 1. If I want to complement a 1, then it will become what? A 0. So 1's complement is actually just handled like that. That if you want to complement this number to a 1's complement, you just now invert. So start from here, Himbo. What would be the complement of this binary number 0111?
It would be 1000.
Exactly. So what about if I wanted to have a two's complement for this number 1011? I need its two's complement. Step 1, I said we get its first what? Its one's complement. What will be its one's complement?
Its one's complement would be 0,
Mm-hmm.
1,
Mm-hmm.
0, 0.
Uh-huh. Then step 2. Remember the question is saying that get its two's complement. Okay. The question is getting its two's complement. Step 1, you get its one's complement. Step 2, add a 1 to a one's complement, to the one's complement of the other original number. So what is our original number? I mean, what is our one's complement that we have got from the original number? It's this one here. So you add now a 1 to that number. So what is the answer here now?
There it would be 1,
Mm-hmm.
there 0,
Mm-hmm.
1,
Mm-hmm.
0.
Exactly. So now, can you try to do for us the number in the PDF? Where is this one? Can we do this number here? So I want to get a two's complement of this number 1001 0, 1, 1, 0. So I want to get its two's complement. Step 1.
Step 1, we have to first get its ones complement,
Mm-hmm.
and its ones complement would be 0,
Mm-hmm.
1,
Mm-hmm.
1,
Mm-hmm.
0,
Mm-hmm.
1.
Mm-hmm.
Wait a bit, 1, 2, 3, 4. This. 0.
Mm-hmm.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Another 0,
Mm-hmm.
1.
Uh-huh. Then step 2.
We add 1 to
Mm-hmm.
that.
So what
Now
would be the answer?
the answer would be that one. Would be, let's first add the one there like that.
Mm-hmm.
So there you said that ideally if we are to add 1 plus 1, it would give us a 2, but
Mm-hmm.
then we cannot write 2 there. So we
Mm-hmm.
would write, we assume there are 2 digits, one and another 1. So we
Mm-hmm.
write 0 and carry the 1 up to the
Mm-hmm.
next figure. So
Mm-hmm.
that would give us a 1,
Mm-hmm.
there 0,
Mm-hmm.
1,
Mm-hmm.
0,
Mm-hmm.
so 1,
Mm-hmm.
1,
Mm-hmm.
0.
Good. So that is about the two's complement. Um, is that clear to all of you? Okay. If you have a doubt, please try to raise up the hand. I can clear it right away. Okay. So please, you just pick up your name and then you tell me the doubt. I'm not able to switch between the windows.
Excuse me.
Yes, please.
Wanted to get a, I've not been I've not got it clearly. Step 2. The twos.
The two's complement.
Yes.
Okay. What's your name, please?
Bernard.
Bernard. Okay. So read for me this statement here, and then we work with this. We work on this number together. Um, yes. Read this section of the two's complement. Mm-hmm.
Whose complement I cannot see here.
Mm-hmm. Two's complement is here. Mm-hmm.
What I'm seeing is yeah, sure. The two's complement of the binary number is obtained by adding 1 to its complement. The two's complement of 1 0 0 1 is equal to 0 1 1 0 1 0 1 0.
Mm-hmm. So, do you know how to get one's complement first of all?
Yes, yes.
Okay. So, for example, get me one's complement of this one here. Mm-hmm.
It is taking a little bit time to display.
No, just speak. Tell me the one's
Which
complement
one?
of this number
This
zero
one,
one one zero. Mm-hmm.
0110. The complement of 0110.
Mm-hmm.
Oh, okay.
One's
It,
complement.
it,
Yeah.
it taken time to display, but 0110, the complement is 1001.
Nice. Now, if I say I wanted not to get its one's complement alone, and I said I want to get its two's complement, the other statement that you just read would mean that after you getting the one's complement here, okay, that would be only step one. Then the next step, step two, would be just now adding a one, okay, to the ones complement of the number that we were given, okay. So the ones complement of this number is actually this one here. So that means that in step two, you would just now bring this number here and add a 1. So you say 1001 plus a 1. Okay? So are you able to compute this now? Can you say 1 plus 1?
You said it's 2, and then you put a 0.
Nice.
And you go with 1. You go with 1.
Carry 1. Then what about this
0,
column?
0 plus 0 is equal to 0.
No, but there is already carried 1.
Okay, so it will be 0 plus 1. Well, that will be 0, 0. That will be 1 then.
And this one?
And this one will be 0. And then 1, right?
Yeah. So this will be the right answer of the two's complement. So if you have understood that, can you again proceed computing for me um, just another number here from random? Can we say we have 11011011? Okay. Yes. Get the get its two's complement.
Its complement will be 0,
So
0.
step one would be
Yes, 1.
uh-huh,
That will be 0, 0, 1.
uh-huh,
Then 0, 0, 1.
uh-huh.
And 0, 0.
Nice. Step two.
Step 2, that will be add 1.
So you get the one's complement above, and then you add one.
Mm-hmm.
Okay.
Yes, so that will be 1.
Uh-huh.
It will be 0,
Uh-huh.
be 1,
Uh-huh.
0, 0, 1, then 0, 0.
Nice.
That's
So
correct.
that is how we do the two's complement. You're now fine.
Sure. Thanks so much.
Okay. Okay. So I hope everyone is comfortable now. Let us move to the decimal complements. So we earlier we said that um, different number systems have their own complements. We started from the two. We said that in the binary base, you have of course one's complement and the two's complement. Then we said under the decimal means that we shall have the nines complement and then the tens complement. So the principle of again getting the nines complement is going to be this: you subtract you subtract 9 from the number to get its nines complement. That is just the thing. So assuming we have a number like 1272, okay, um, for you to get the nines complement, and then someone tells that find its nines complement, okay, this would be the rule: subtract subtract a 9 from, I mean subtract each digit, okay, subtract each digit, subtract each digit from a 9, and then the answer would be the 9's complement. So in this case, this is the number which is in base what? 10. And we want to get its nines complement. What would we do? We would get a 9, subtract from the first digit, which is what? I'm starting with the MSD, going to the LSD, okay? So I would have a 9 minus 1. I again have a 9 minus 2. I again have a 9 minus 7 and a 9 minus 2. Then the answer would be what? The answer would be 8, 7, this would be 5, and then what? 7 in base 10. This will be the 9's what? 9's complement.
Excuse me, sir.
Yes, please.
9 minus 7 will give us 2.
9 minus, okay, yeah, thank you for that analysis. That is so right. So this will be 2, okay? Yeah, so this will be the answer. Um, what about if we had this number in the example? The example is having 2496 base 10, and I want to get its nines complement. So its nines complement would be 9 minus 2, it should be 7. 9 minus 4, 5. 9 minus 9, 0. 9 minus 6, 3. So this would be the nines what? Complement. Um, yes, let me proceed with the tens complement. The tens complement now will just be like the same approach that we used in getting the twos complement. Remember, in the twos complement, you get the ones complement and then add a 1 to the ones complement. Also, when you were getting the tens complement, you first get the ones complement, then add a 1 to that nines complement. So in this case, if I had a question that find a tens complement of 2496 base 10, I would first of all, step 1, get the nines complement. That would be 7503. Then step 2 would be just what? Adding a 1. What number do you get if you just add a 1 to this number? 7504. And this will be the answer. Is that clear to all of you?
Yes.
Okay, great. So actually we don't have to suffer a lot in knowing the rest of the complements. So now the approach is the same as we have done in the in the tens complement and nines complement. For example, if I say I want to have maybe to look at the octal base, and we know octal base is base 8, okay? Maybe I could have a number like 271, and this is in base 8, and I say I need the sevens complement. What I would do, I would subtract a 7 from each of these digits, like this. And then the answer would be my sevens complement. This will be 5, this will be 0, and this will be 6, base 8. This is my what? Sevens complement. But if I want to have the eights complement, then step 1 would be get sevens complement, and step 2, add a 1 to the sevens complement. So in this case, I already have this one as my sevens complement, the 5 um, 507, it means that the 8 complement would be what? Just adding a 1. So that would be 507 in base 8. This would be my what? 8 complement. Let me now get the example in the PDF. Please, if you have a question, just raise the voice and then speak your name. I'm not
Uh,
able to go.
Komhimba Bagonza,
Yes, please.
there's something I've observed when
Mm.
you talk about, let's say, the nines complement or the eights complement. It seems like the answer you get shouldn't be, the figures shouldn't be greater by the figure on the complement. Like, for example, the numbers we've seen, if we are looking for the eights complement, meaning we cannot get a value with figures that are greater than 8,
Yeah, but
like that's what I observed.
also the other principle might be that you cannot have a number, of course, which is exactly the same value with the base number, with that base number. That would be also a factor. But as long as you have gotten the principle, then I'm good to go. So if we have a number like 562 base 8, and I say need its sevens complement, then this sevens complement would just be subtract a 7 from each of these digits. That would be 7 minus 2. I mean 7 minus 5 would be 2. 7 minus 6 would be 1. 7 minus 2 would be 5. So 215 base 8 would be the 7's complement. Yet, if I say 8's complement of this number, means that I had step 1 I got my 7's complement. Then step 2 would just be meaning I need to add a 1 to the 7's complement. What is the 7's complement? Was 2158. So add a 1. I will have 216 to get my um, 8's what? Complement. Okay. The last group of complements is the group of 16. The group of 16, of course, we know that this is base 16. It means that in this you only have 15's complement and 16's what? Complement. So this one has a special case. When we are counting in hexadecimal, this is what we do. Just add this knowledge to that, then you'll use the same principles as you've done in the sevens, eights complement, okay, and tens and nines. But this I say, for example, number starts from 0, 1, 2. I'm counting in hexadecimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. When we reach 10, we don't write 10. When we reach, when we have 11, we don't write 11. We don't write 12. We don't write 13. We don't write 14. We don't write 15. Of course, we don't write 16 because this would be now superseding the number of what possible digits in that number system. So if a number system is 16, then you cannot include 16 inside it. Okay, but even the 10, you don't write a 10. So you switch now to the alphabets. So start with A. So instead of 10, you write A. Instead of 11, you write B. 12, you write C. 13, you write D. 14, E. 15, F. Okay, so having mastered this, let me go back to our example. Okay, let me just have maybe a simple example from this side. So assuming I say my hexadecimal, okay, before I go that side, I again wanna tell you one other thing. If I'm writing a hexadecimal number, I add this prefix 0x and then the number. For example, if this is supposed to be my hexadecimal number, then someone would only identify that it's a hexadecimal number if I don't write it just as a mere 4 like this. Okay? If I write it like this, that is only when someone will understand that this is an hexadecimal value. But this one now, someone would think it is maybe a decimal value. Okay? So you would maybe most of the times see me write something like that. Okay? Maybe 0x, maybe 2 7. Okay? So I think that is clear with you guys. Now, assuming we want to have now to look at the 15's complement, we don't now differentiate from the other rules that if I need maybe a 15's complement of this number, a 15's complement of this number, I'll subtract, which is step 1, subtract um, each digit from 15 and write the answer. Then, yeah, that would be the only step. So in this case here, I would say 0x, just to show that this is a hexadecimal number. A is 10, so 15 minus 10 will be 5. Then you have 2. 15 minus 2 is 13. And what is 13? 13 is a D. So you don't write 13 here, no, you write a D. In base what? 16. So this is the hexadecimal number, okay, as a 15's complement. But assuming I wanted to proceed in getting the 16's complement, again the rules stay. You get the number of the value, because this was the original number 0xA2. Its 15's complement is 0x, I mean is 0x5D. So I add 1. So add 1. Adding 1 will be meaning what? 5 to the 5D. What will you have? Of course, we are adding that 1 always to the least significant what? Digit here. So a 1 plus this, what will be? What will that be? It will be, it
E.
will be 15. So it will be E. So you have 0x5E. So this will be the 16's what? Complement. Okay, let's go back to our PDF and do that example. Okay, so we have a number 3BF. We said we agreed that you can write it as this and don't even have to put now the base here if you write the 0x, because you clearly have told me that this is what? base 16. Um, so the 15's complement would be what? It would be 15 minus 3. Someone could interact.
15 minus 3 is 12.
And what is 12 in the, do I write 12?
C.
Is it C? Uh-huh.
C.
And then what is a B? Uh-huh.
11.
So 15 minus 11.
4.
Uh-huh. So you write a 4 here. Uh-huh. This is 50. This is 15. 15 minus 15.
0.
If it was 16's complement of this,
Uh, 0 x
uh-huh,
c 4 1.
0,
0 x c 4 1.
0x c
C 4
4 1.
1.
We have this other number 2 um, 2AE, and we need its 16's complement. Uh-huh. What would you have? 0x 15 minus yeah, yes, because you minus 2.
13.
Are you sure? 15 minus 2, 13, yeah. Okay, and what is 13?
13 is A B C C.
It is C. Uh-huh. And then 15 minus A, which is 10.
10 is an A. A.
5.
Is 5. Mm-hmm.
Minus C.
Then what? You said 3?
Which is a 1, yes.
Okay, so what answer do I write here?
13, hello.
Mm-hmm.
13 is D, not C.
Mm-hmm. So you guys contribute well. Uh-huh. Someone should just dedicate themselves, and the others keep quiet, please, to avoid the confusion. So who is contributing?
Andrew.
Mm-hmm. Andrew, go on, please. Uh-huh.
We are getting 15's complement, right?
Mm-hmm.
So you subtract 15 on every digit.
Mm-hmm.
So we get 0x.
Mm-hmm.
15 minus 2, that is 13, which is a D.
Mm-hmm.
Then 15 minus A, which is A is 10, that is 5.
Mm-hmm.
Then 15 minus E is 14. That is 1.
It
15
is 1,
minus
huh?
is 1, yes.
Exactly, huh? So this is very true because I know the the 16's complement, you just now add a 1 to the least significant digit. So the 16's complement means that when you add a 1 here, you will get this answer here. Okay. So the answer will be now this one here for the 16's what? Complement.
Yes.
So, I want to give just a break before we go to the numerical representation. A break of just maybe 2 minutes. You guys take some water, then we come back. When we come back, if you have any doubt you want us to clear, we can discuss. No problem. Don't leave the meeting, please. I hope we are all on now. Yeah, so can I have any questions from you guys?
Hello,
Yes, please.
my name is Ronald.
Yes,
So
Ronald.
my question is, like hexadecimal, we stop on F, which is 15.
Mm.
So if we have, let's say, F plus 1, what
Mm.
does that become?
When we say,
Let's say F plus 1 in hexadecimal.
mm,
What does that become? In the twos, in binary, 1 plus 1 would be 1 0, because you can't say 2. And also, uh, now in hexadecimal, we cannot say 16.
Mm-hmm.
So I'm wondering what f plus 1 becomes in hexadecimal.
So um, you're looking at a situation of where you have zero, um, a, and then you say f.
Yes.
So this is not actually possible. You ask me why.
Okay.
So
Well,
ideally, implicitly this is 15, right?
Yes.
And the step of adding a 1 would only require you, if you wanted to compute for a 16's what? Complement. So that means that you should have had a 15 somewhere, subtract the digit that was here for you to have gotten the 15. So and in that very number you could not have maybe a 16. You could not have a 16 in hexadecimal. So that is not possible and it cannot appear.
Okay.
Yeah, you get the meaning.
Yes, I'm following.
Yeah, you can't have you can't have because it is not there. You cannot have such a number as a hexadecimal. So if you can't have this, then you cannot go on computing with that. Andrew, you have a contribution, a question, or what?
so it's a question.
Mm.
I just wanted to know where is this applied because it looks. Just wanted to know where it's applied. Just
Right. Okay, it's a good question. So you guys, you're doing programming. You're doing Python. You're
yes,
doing
we are.
C, C++. So um, the computer receives what is called zeros and ones as the machine what? As the machine code. But when it receives this, anything that is received on memory, because you have your memory somewhere. So assuming you have your memory somewhere, and I've written maybe my code like int x, maybe I stored a 9 to there. This means that x would be a variable, but this variable is going to store this 9 but inside a certain amount of memory. So depending on the machine, this integer could either be 2 bytes, okay, or even 4 bytes. Now you reach a situation of where you have maybe you need to maybe use something like characters. Character is also a data type, okay? Character is a data type, but maybe at some point you wanted to store a negative value, a negative value of maybe negative 120. So how would you store this value of negative 20? Is by use of a complement. So the computer uses complements in storing negative values. So that is how the complement um, concept is important. So you, as the programmer, you need to know these concepts. When you're doing your programming later, you get um, you'll get the meaning of this, and then maybe the real use. Is that fine? Later, you'll see that computers actually um, use representations of negative and positive values in three ways. The first way is called the sign bit magnitude. Second way is the ones complement. Third way is the twos complement. As technology go on, you can see where actually you can use the 15's complement. But most commonly, we use the twos complement, and the formula is actually negative 2 to power n minus 1. So this is the range to a positive 2 to power n minus 1 minus 1. So in example, you guys have maybe looked at your machine and you see that your machine can maybe store up to 64 bits. Some machines can have operating system that can store data up to 32 bits. This only means that you are going to now compute into the other formula. Just now imagine that your computer could store into this range. So assume is your 64, so this will be 64 minus 1, okay, to a positive 2 to power 64 minus 1 is of course is 63, and that. So who can compute for me the value? I think these are millions of ranges. Who has a calculator there? All of us. I think mine is not so near. Do you see that is a big number? I'm actually seeing something like a negative 9.22 times 10 power 18 to um, what? To again, of course, this minus 1 to 2.2. Of course, I've rounded off. I've rounded off 10 times 10 power 18. So that means that whichever number you write inside here will be fitting in your what? So your computer, which is a 64-bit, can store data within all that range. So Andrew, that's a programming concept. You'll thank me later. I think you're getting maybe the highlight. Okay. Is there anyone who is requiring something? What's the problem? You have a query? Jeannie is wondering, Fahad is wondering, Dennis is raising his hand. Okay. Hmm?
Yes. Hello.
Yes, please.
I didn't
Uh,
get that one.
I'm still wondering where. I remember there's where we got a 0x5e.
Where?
What did from
Which
the
number?
where we started when we are doing the complements,
Which complement? The
the one
twos
of
complements, the ones, the twos, the
I think
which
we are on the complement of 15.
mm,
There's where you wrote 0x5e.
mm, mm. Yes,
Then I
what
was wondering that 0x what does it mean?
So you will see later, you will even write a binary like this. Okay, or
Yeah.
sometimes they just write the B because B means what? Binary. Like ideally, B means what? B stands for binary,
Yes.
and the X here, 0x, the X is again from the hex decimal. Are you getting the idea?
I'm getting it.
Yes.
Okay.
Okay. Yes, please.
Yes, just maybe a little to where the two complement, where there is a 1101111.
Where? In the ones complement.
After add the
Hmm?
yeah in the one complement. Yes, yes.
What is the issue with the ones complement now?
After the two's complement.
After the twos complement or the ones, which is which?
I mean after the one's complement. Yeah.
After the ones complement, we went to the twos complement. Didn't you understand the concept of the twos complement or what?
Yes, I failed to understand the second one. Yes.
But were you in the call?
Sorry, I just came in the middle of the
So
class.
you will watch it, you will watch the video because we cannot go back in and out, in and out. It means that you either was not in the class or you were sleeping. I don't know. But these are things that I've tried to explain many times. I don't know. Is there a colleague who wants to explain to a fellow student? Maybe they can understand better. You could raise up your hand and then explain. Even that will help you also understand more. He wants to understand how to compute the two's complement. Yes, Michael.
Yes, sir. Uh,
Mm-hmm.
I think first of all, before you get the two's complement, you have to get the the one's complement. Then after getting the one's complement, now you add one to the
So
one's complement.
assume for us an example as I write for you here.
Yes.
Mm-hmm.
Uh, like for example, 1101
Mm-hmm. And the
11.
questions may be saying that find its what? Its two's
It's
complement.
two's complement.
Mm-hmm.
Oh, first of all, you get the one's complement. Now it
That
will
is
be
step one.
step
Mm-hmm.
one. It will be a 0 0
Mm-hmm.
1 0.
Mm-hmm. Then
So
step two.
step two, you add one to
Mm-hmm.
the one's complement.
So the one's complement plus a one, which is
Yes,
the 0 0 plus 0010 plus a one.
one.
Uh-huh. But in binary addition, what did we say? Uh-huh. So 0 plus 1,
It's a
it's a
one.
1. Uh-huh. And
Yes,
1 plus a 0, 1,
it's a one,
and a 0,
0,
and a 0.
0.
Okay. So is that now fine for the colleague?
Yes, sir.
Okay. Yes, Michael.
Thank you.
Yes,
Thank
sir.
Michael, you're raising your hand.
No,
Fahad.
Yeah, I was just saying, does it mean in binary when you're adding, it's not like the normal math we understand? Because when I say 0, 0, 0, 1, 0 plus 1 would have been 1, 0, 1, 1, 1, 0.
Yeah,
But
we
here,
are we are
it
already in a computer language. We don't add as the normal adding. The normal adding stops on decimal. So as the humans add in decimal, humans add in decimal. Okay.
okay.
Yeah. You guys, if actually you have calculators, these calculators I think are also able to add in binary numbers and maybe hexadecimal and octal. I think when you try to, do I have to use shift or alpha? I'm seeing my scientific calculator actually has those capabilities. But like your question said, in binary addition is not the same addition as the decimal. For example, I said that if I was adding a 1 plus a 1 in binary, okay, in decimal I would be having a 2, but we cannot write 2 in binary. We have to write it in binary. So 2 in binary is what? Is always a 1 0. Okay. You will later see how I get this anyway. So if I have a 1 0, that means that I add a 1 here, maybe a 1 and a 0 here. This is what I was adding. So 1 plus a 1, I'll now write 0 instead of the 2. So I carry 1 to the other end. Again, I add 1 plus a 1, I get a 2. I don't write 2, I write 1. I mean, I write 0 and carry a 1. Then again, I bring a 1 here. So this would be what? 100. Okay. So that is totally different from the decimal or the normal way of counting. Is that now clear?
Yes, sir.
Yeah.
Okay. So yeah, this is now about the number representations in binary. Aha, it is good this concept has come here. So Andrew, please look at this point very well. Methods of representing negative and positive decimals in binary forms include sign bit method, ones complement, and another one is two's complement. So we are going to start with the ones complement, I think. No, we are going to start with the sign bit method. I had already told you about the MSB and LSB. Who is not aware of the MSB and LSB? Who cannot be able to identify the LSB from here and MSB? Who is not aware? Jalia, yes. Can I interact with you, please? So where is the MSB and where is the LSB?
I don't understand how to get the LSB and MSB.
Okay, but do you know what MSB stands for?
No.
Uh,
No, sir.
so let me give a scenario. Let me start with the normal things that you guys know. If someone was demanding you 50,000, I mean, 50, yes, 50,000, uh, 521. Um, I said 50,521. um, how much would you give to this person? And he assumes that you have totally cleared him.
You would give him 50,000, either 600 or 50,000 500.
Okay, that is okay.
Uh,
But
to me,
assuming
I
you
will,
don't want, assuming you don't want to exceed the amount, you
to
just
me, I
want.
will give I will give him 50,500.
Aha, 50,500. Would you tell us the reason why? You're right, but would you
Yes, sir.
give me the reason? Hmm.
I
There's
thank
no way
you.
you can get 21 shillings.
So that means that this one is almost written off because you are like, it doesn't matter, okay? It doesn't matter. You get the idea. So if the 21 doesn't matter, what side is it at? Is it at the left side or at the right side?
It is at the left side.
Aha. So digits that are always at the left, at the right hand side, they become more and more insignificant if in this scenario maybe the 2 was this side and then this value would be 2 1, okay, and the 50 in this case may be shifted to the other side. Let me actually write like that. How much would you give him? The scenario would change, yeah. You would maybe even give them this amount and still you guys would remain friends, right? So that means that anything that shifts to the left side, it becomes more and more significant. So when we say most significant digit, most significant bit, we assume the context from the left hand side going to the right hand side. So in this case, when I say MSB, I mean bit, most significant bit. If I say MSD, most significant digit, okay? Then this will be LSB. The other side, LSD. So now, is that fine now, Jalia?
Yes, that's okay.
Okay. Okay, so so let us now look at the methods of how you can represent uh, the, the binary if you want to show it as a negative or as a positive, depending on the range of the bits of the bit width. So let me start with this method, sign bit. When you see 0 on a bit that you are going to be looking at, on the number that we're going to be representing, 0 denotes that that number is a positive number. But when you see a 1, it represents that that number is going to be a negative number. So the remaining part of the number will be now the real number of or the real magnitude of that number. Okay. Now, assuming you have this number, yeah, let me just have a 4-bit representation. What does this number tell you? This number will tell you that this is a positive number. This number will be a positive number because of the 0, which is an MSB. That means that the rest of the number here will be the magnitude, will be the real number. So you just have to know that now, whatever number this is, the binary, which is 110, is now the real what? Magnitude of the number. If this one was 1, 1, 1, 0, that means that this one will be the real number, the real magnitude, but this one will tell us that this number is a negative. Okay? In this situation, the example is dealing with the 8-bit representation. Why 8-bit? This is 1, 2, 3, 4, 5, 6, 7, 8. So the MSB here in this case is this first zero from the left. It tells us that this is a positive what? Number. Then the rest of the number from this one here to the other side gives us the real value of the number. So this value here is 7. I mean is 9, okay? This value here is 9. And it is 9 but a positive, okay? When you look at this other number here, it is a 9, but because of a 1 here, it is a negative 9. So that is how the sign bit magnitude um, operates. But we have now a rule to represent the decimal numbers in their range. So if it is, yes, Jalia,
Where did we get the 9 from?
that is when we are going to look at the conversions. You will understand where the 9 comes from. That first keep that one. First keep it, because if I now bring in the conversion now, you'll get confused. First get the concept, then you'll connect later. Okay?
Okay.
So I want to first visit a book here and I see if they have some other um, some other examples. I want to visit a book here. Okay, I thought I could find an example here, but let us proceed. Okay, for number conversions, to complete this. Oh, okay, this is what I was looking for. Okay, my back. You ready to hear my voice? Okay, so I was first of all looking at the sign bit magnitude, and we of course saw how important the zero is if you see it as the MSB, and we say that on such a number, this will just tell you that if you look at this MSB, tells you that the number is a positive, and the rest of the part will just now tell you the real number. And if it was a 1, then the number would be a negative. And we're saying that we have a rule which helps us in defining the ranges. And this rule is giving us a formula which is 2 to power n minus 1 here, 2 plus 2 to power n minus 1 minus 1. This is the formula. So where does this formula actually help us? Yeah, this just helps us in understanding that depending on the on the type of machine that you have, how large data you can store on your machine. So if your machine maybe can store only 4 bits, okay, it can store only 4 bits, then then that means that n stands for the 4 as the value. Then using this formula, you will have that range as 2 to power n, which n is 4 minus 1, then to a positive of 2 to power 4 minus 1. That will be 2, this will be now 2 to power 3, which is 8, 8 minus 7. Then that will be what? I mean, 2 to power 3, 8 minus 1, which is 7. So negative 7 to what? Again, this was what? To positive 7. So in that case, that will be the range if your machine can only store up to 4 bits. If it is 64, then again, same thing, compute the 64 into that. Um, that is about if it was a 4-bit representation. If your machine could now store something like 8-bit only, what range would you have there? Then again, calling this formula is for the sign bit. You'll have 2 to power n minus 1 minus 1 to a positive 2 power n minus 1 minus 1. So what is n? N in this case is 8 minus 1 minus 1 to a positive 2, n is 8 minus 1 minus 1. This is 7 minus, this is 2 to power 7. What is 2 to power 7? Is it something like 128? 128 minus 1, which is now what? Negative 127 um, to positive 128. So this one will, this is not actually one, this is not 128, this is 127. So sometime in your programming, you understand that you could maybe have to store like unsigned car, and maybe this character is a variable x, which wanted maybe to store um, a range of what? Um, mm, Maybe you wanted to store 120. So that means that this 20 can be able to go within this range. So if you wanted to store something like 130, then you always receive an error in your code. Yeah. So that is how those things will be very important, like Andrew asked earlier on. So that's about the sign bit representation. What about the ones complement method? The one complement method, of course, you know idea that to complement something like this, you will have something like this if it's a one's complement. Okay? If it's a two's complement, then we shall later see. But later, still the rule of the 0 and the 1 stands, that if MSB is a 0, then this number will be a positive. If MSB is a negative, is a 1, then this number is going to be a negative. But the number is now this one here. I know this number 111 is a 7. This one is a 0. We shall later see how to convert. And the formula is again the same, like the one of the sign bit magnitude is the same as this one for the ones complement. I think it is only going to differ a simple little different from these ones when we reach at the tools complement method. Yeah, so that's the rule. Then when we reach on this other method of the tools, of course, that is one reason as to why we first understood how we can compute the two's complement. That first of all, you need to first of all get the one's complement. In this case, if you have such a number, the one's complement will be something like 1001. Okay, and then the two's complement, you'll get that one's complement and then add a 1. In this case, 1001 plus a 1. What will be the answer here? Who can contribute? I see if uh, someone is not yet lost. What is the answer here? And someone
0,
0.
1,
Mm-hmm.
1.
Are you sure it's a 1 again?
Sorry, 0,
Uh,
0,
uh-huh.
1.
Yeah, like that. This will be the two's complement. So we want to see what now um, what now this states in terms of the what the formula. In terms of the formula, the little change in the formula is now this. Let me just decrease this a little bit. In this case here, it is a plus 2 to power n minus 1 minus 1 to a positive 2 to power n minus 1. You don't now again subtract the 1 um, again after the exponent. So the other two, the formulas were like this: 2 to the power n minus 1 minus 1. Uh, of course, this is a negative, not a positive.
It is negative.
This is a negative, and this is a negative, to a positive 2 to the power n minus 1, again minus 1. This one was working for the sign bit magnitude and the one's complement method, okay? But for the two's complement, you use now this what? This formula. And I've shown you where the formula work, okay? So I'm taking you so fast, but the good thing is that I'm
Excuse
recording
me.
this session. Yes, please.
They look the same. It is from negative to positive, all of them.
Which one looks the same?
The first one up and the last one down. The
Be keen.
formulas.
Be very keen. Something is different. When I subtract the n minus 1 here, I don't include the minus 1 here after. That's the difference.
Oh, okay. I've seen it. Thank you.
Yeah. So, um, our next now business should be how to convert from now the decimal to binary, from binary to hexadecimal, from
Excuse me.
hexadecimal
Another
to octal.
question.
Yes, please.
In the PDF, I see it is from positive to negative,
Then that should be a mistake. It should we come
but
from
then
the
you
other
wrote
side.
from negative.
That should be a mistake. But either way, it's a range. It has to be running from the negative to the positive. Either way, how you write it, as long as they don't have the same signs, that should also be the same. It's a range, okay? So I was saying that we have now reached at the point of number conversions. And according to our time, we had agreed to meet from 4 to 6. It is just 6 now, just 1 minute to go. So I cannot take you anymore, but I think I would request you for maybe 1 hour, and then I take you through the number conversions, and then maybe up to the level of the level of the day students. But to help you again catch up, um, as we organize that makeup class, I'm going to share the recordings of these classes. I'm going to share you the day recording uh, up to where I also covered the number conversions, and I also share your recording of today. Yeah, so when you go through and you also go through the class that I took them through the number conversions, you'll be able to do the self-reading and self-catching up. So I request for maybe 1 hour within the week. You guys can suggest, and then I just maybe come, we discuss where things have not worked for you so well, so that you don't lag behind. Because now the day students, I think they are somewhere. Let me see where have they reached these guys. Let me actually stop this recording. The students have reached somewhere. Okay, they were about to complete the conversions, but also they didn't complete so well. But at least they are a little bit ahead of you. Yeah, so I'll need just 1 hour to just make up with this. Not today, but anytime within the week. Yes, so you guys can suggest. Yes, Michael, you have a comment? What you have?
Thank you very much. I'm looking at the time we really spend on Saturdays from morning to 10. And
Mm,
I wish if we could use around 1 or 2 hours while waiting for other classes to start on Saturday to be better.
okay, okay, I'll take note of that. Yes, Paul. Mm, mm-hmm. From what time to what time? Oh, okay. Uh-huh. Can I hear another scenario? Yes, Bernard.
Yes, I think we can do within the weekdays, probably from Tuesday, maybe evening.
How about a Friday? Because it looks like a Friday. We are not having any lecture.
So, first of all, we are getting issues because I think the timetable is over changing. So I've been getting many inboxes. Different students are giving me different timetables, and I also have a different timetable. So I have a timetable for weekend students doing digital electronics at 10:15 to 12:15. Then someone again yesterday tells me that no, the timetable has changed from that time to two, from two to four on Sunday. Another time, someone is going to come up with another timetable. So, uh, myself, I thought that Saturday you guys actually were free, but now again, someone is telling me that some other students are taking what? Are those the ones doing bachelor's or diploma who are covered with Saturday? Because from my end, unless you guys tell me that you we can fix this class. I mean the common class now, the normal class. Now I'm not talking about the makeup class to cover any lost thing, any lost time, but the normal class. If we could have it from 8 to exactly 10 uh, during Sunday, do you have any people who are covered by that time? I'm now setting the usual class. Instead of having it from 10 to midday, can we push it early in the morning, like from 8 to 10? Is it possible?
Yeah, I think 8 to 10 on a Sunday will be favorable.
On Sunday it's a bit hard because we go to prayers, in the morning.
Yes, brother, I understand. You guys are going to pray. I myself, I'm also going to pray. But now you are weekend learners, and you're also distance learners. So if we fix this time and we say that okay, we have 2 hours for this digital electronics, that means that the rest of the day you guys can again fix these things. Yes, Paul.
I'm supporting Paul's submission because that time would favor some of us.
I think I concur with that submission.
So can we agree that we take the class from 8 to 10, exactly 10? So if we agree, I myself would want to join the class even at around 7:45, such that by around 9:45 we are concluding, because I'm also having also other engagements, again which are again academic, from 10 to again other times of the day. But I was also trying to sacrifice, because the original timetable was telling me to take you through from 10 to noon, but you guys I've gotten many timetables. So if we can agree 10 to, I mean 8 to, hey, did we say 8 to 10? Yes, let us take it from 8 to 10. That would be just fine. Yeah, no need again to say 9:45. So the class will always be from 8 to 10, such that if there are any other maybe classes that I'm not clashed within after, then you guys can take them on. But of course, most important that I'm going to be always recording these classes and can share, and you guys can catch up. Yes, Fahad, can I hear from you?
Well, good evening, sir. I was just trying to inquire, are we changing the timetable or we're trying to fix up a session so as to go through what we are missing so that we are the same level with those doing daytime?
We are fixing the timetable because we have different timetables altogether. We are just fixing the timetable for the normal class at the moment. Yes,
Okay.
Michael.
Yes, thank you, sir. To me, I concur with the suggestion because always on Sunday from morning to 10 we don't have a lesson. Now that means we can utilize that time very well.
Mm.
Thank you.
Okay, so I'm actually writing it on my timetable here now officially. So you guys now next suggest the makeup time. Suggest the makeup time, and that makeup time, of course, shouldn't be during day, because I'm again teaching other courses throughout the day. So we can look at maybe You guys can suggest maybe an evening, things like that, and we see what to do. But Sunday is now just for the morning class, which is from 8 a.m. to 10 a.m. Okay? Yeah. So please contribute.
I would suggest Friday evening.
That is one suggestion.
This these suggestions that includes calculations does not require uh, a evening. It needs very early in the morning when we are fresh.
My friend, what is your name?
By the way,
This is my
uh,
concern.
does it, does it mean we are not going to have meditation like on peak hour
So,
every day?
so you guys are funny, but that is just a mindset, I would say. You can do actually calculations are very good when you're actually tired. They are more of something that can raise you up. But if you are reading something which is just essay formatted, assuming you are reading communication skills, do you think you'd read and understand it when you're tired in the evening? Hmm? I think calculations are just fine at any time. Yeah. So let us not look at that. Let us look at just when we can have the time and is not clashing a lot with your other classes.